okay. No charge can stay inside a conductor, only an insulator. Can you get that? Okay, and let's say you have a point P here, right? And you want to find what's going to be the electric field here. So you need to cut this volume in small pieces. So it's a volume, right? So we're going to have a little volume here, dV. And remember from calculus class, for example, it could be dx, dy, dz, or sometimes you can use the polar notation or the cylindrical or spherical notation, spherical coordinates. So anyway, you have a little dV here. Inside that little dV, you're going to have a dq. Okay, so dq, it's going to be the density times the volume. And this is the charge density, rho. Okay, so it means it's the charge per unit volume. Okay, and the volume is the whole thing here, the volume there. So once you have that, and you are located at position R, I'm going to call that R sub I. Okay, so you see, you're going to have a small dE, so a small electric field here just produced by that one. And then you need to go to the next one. You have to scan inside and you have to do it in a smart way. But then you go here, that distance will change there, and you're going to have also another dE. Not the same, right? Maybe that's going to be dI. This one is going to be dI. This one is going to be dJ. Okay, I'm just giving you the idea. Okay, it's not the same dE. They don't have the same magnitude because they don't have the same distance and they don't have the same direction. And you have to do that for everything inside. So usually it's done by your computer, except when you have a nice symmetry, like the disk or the ring or the line. Once you have done that, okay, you have to say that the sum, so you need to add them up, okay? So you add them up, okay, maybe it's positively charged inside. So you're going to have a lot of dE from every single little volume, dq, right? So add them up, you know, tell to hey, the parallelogram, you add them up, and then you're going to have E net. That's the goal. But because it's continuous, the sum will turn into an integral. It could be a line integral if you have a linear distribution. It could be a surface integral if it's distributed over a surface, or it could be a volume integral. So three integral, triple integral. So that will be the sum. So usually you start with the sum. So I'm going to start with the sum. So that will be the sum of all the little dE. So it's a vector sum. Okay? But because it's a vector, you need to divide that into components. So you have the x component that will be the sum of all the little x component, right? So it's a magnitude. And you have the y component, which is the sum of d a y. Okay? So I'm trying to get you to the idea. So once you have done that, you see that the x component is going to be the sum. X component will be the magnitude. It's always the magnitude. And it could be a cosine, depends. I'm writing cosine if you go from the positive x-axis to the vector. So then you can say you are using cosine. Sometimes it could be sine, depending on how you do it. So here, let's say we're going to do sine. Okay, so once you've done that, you need to find the magnitude dE. Okay, so the magnitude dE, okay, I use Coulomb's law. It's the force per unit charge, so it's going to be the constant. That little dq, and then the distance square. But that distance will change. So then the goal is to find one single integration variable. So you need x. So for example, you want x here, x there, or z here, z there, or y here, y there. Okay, so then you can integrate. So these two, okay, will become the sigma integral means sigma. It means a sum. So it becomes a sum. So it's going to be k dq. And then here you need to find the distance, okay, for each single one. And maybe there will be a cosine. And you need to find here the limit of the integral. Okay. And that's going to be, in that case, it will be a triple integral because you are integrating over the volume. But that you cannot keep it this way. It doesn't look good. You need one single integration variable. So you have to work on that. You have to massage and malax. So then you can integrate. There will be just one single problem on the test one where I am asking you, just to set up the integral, not to solve the integral because I forgot how to do it, so I cannot ask you to do it, but just to set up the integral. Is that clear? Okay, so then if you need examples in your book, let's look at your book. Again, it's a very nice book, University Physics. You can get the PDF. Okay, so it's chapter 21. And so this is not continuous, it's discrete, but the same idea. At a given point, I need to find the vector sum of those two electric fields. This one goes toward the minus because imagine you have 1 coulomb of charge here. That's how you find the electric field. You have 1 coulomb of charge placed at P, and this one is repelled, so you add them up. In that case, you see that the y component cancel out, so you have only the y component left. Now, if you go down, they tell you how to do it with integration. So in that case, you see the y component cancel out. So you're going to add all the x components. So first you're going to find a dEx, and then you have to integrate. Okay, so in that case, you have to look at it. Okay, it's a good practice for engineers. You see, they were able to find the variable of integration, which is ds. Okay, that little segment, line segment. So if you integrate around, okay, so if you integrate is the sum, if you sum up all those ds, you're just gonna go find the distance around. Okay, so 2 pi r. So this one is easy. So you should do it on your own and hide. And in that case, so it's not infinite. Okay, so it means you cannot use the equation from your equation sheet here. This is a line. Where is my line? But it's an infinite line. Because if you have infinite line, that means only the y component will stay. In that case here, and then you will take the limit, but in that case here, it goes from minus a to a. You see that the variable of integration will be y, and y will go from minus a to a. So in that case, you're going to have an x component and y component, and you see you have to, it becomes like kind of a headache, but you have the x component and you have the y component. You have the variable of integration, and that's what you find. And then when you take the limit, okay, so instead of having a finite line between minus a and a, then they take the limit when a goes to infinity. So now you have a very, very, very long line, and you get the same answer that we found, the same answer that you have here for a line. So this equation works for an infinite long line. Okay, but it's a very nicely done because it's a good exercise, and you see step by step how it's done. If you bought the book with Canvas, you know they have embedded a video to show you things step by step. Okay, here you have the disk. So same thing, you have to integrate. So it's a good practice, and at the end, you see that's what we found last time. If you are very close to the surface, so very close to a charged surface, so at some point you take the limit, so it means x equals 0, or x is very small relative to the size, so you are very close to the surface, then you get this equation. And next time I show you a demo to prove that if you are not very far from the surface, the electric field is constant. It does not depend on the distance, and it's just the density divided by 2 epsilon 0. And if you are very, very, very far away, everything happens like you just have one charge. And then you say kq over distance squared. Okay, so again, you cannot survive, you cannot take the most of it, of this class, since you are stuck here, unless you open your textbook. So it's just short review. So last time we found that if you have a surface, so it could be like aluminum foil, okay, that you charge. Let's say you charge an aluminum foil, very big, very big, very big, very big, very big, very big, positively. You charge it because maybe you connect it to a Van Graaff generator, right? That's what the demo they did. So it's connected. This is a conducting wire here, so it's all charged. So you have an electric field here, because this is a source of an electric field, goes on both sides. So you said the electric field is uniform. So the lines here are equally spaced, so it's all uniform. E. And then if you are not very far away, so if the distance here, that distance here, so if the distance here is small relative to the size, so you're not very far away, the electric field does not depend on D. It's going to be sigma over 2 epsilon 0. Okay, and sigma is the charge density, so the charge divided by the area. So that's what we did last time. It doesn't matter the shape of the surface, could be a disk, it could be a rectangle, whatever. But the electric field goes both sides and it's uniform, constant. Okay, so that's why it's equally spaced. Okay, one thing to keep in mind is that if you have a conductor like this, a Van Graaff generator, and it's charged, it's forbidden to have an electric field inside. So if I take that aluminum foil and I make it like a closed back, I close it. Okay, so it's called like a Faraday cage. Inside, we're going to see that, but inside the electric field equals 0 inside. You cannot have an electric field inside, it's forbidden. Okay, so if I take this aluminum foil and make it like a bag, inside you cannot have an electric field, right? So the electric field will go diverge out. Okay, so that will be your electric field. Okay, so you see here is sigma 2 epsilon 0, but here you cannot have an electric field. So now we're going to see, we can prove that with Gauss law. So Gauss law is just a mathematical tool to solve for the electric field, like when you have a very nice symmetry, like a spherical symmetry. So in that case, the electric field will be sigma over epsilon 0. But it's the same thing. If I just very close, if I'm very, very close, not far away, very close. Okay, because the electric field equals 0, we're going to see that with Gauss law. Okay, so it's a review. It's very important to understand the concept. Everything else is just math. So very, very important. The concepts are very important. So anyway, we came to this result. You have an infinite surface. Okay, you see the electric field is uniform, and that will be the equation for the electric field. Okay, and if you look at your equation, it says shit here. Sigma over 2 epsilon 0. I have to watch my accent. Okay. Okay, and that's a constant. Okay, so we did that. So now we can go back to the capacitor. So what capacitor is just a way, it used to be a Leyden jar, so it's a way to store charges. So you have two electrodes Okay, one is positively charged, one is negatively charged, and you have an electric field in between. Okay, and if you have too many charges, you can have a breakdown. So what is the electric field doing is trying to bring plus with minus. So an electric field, you can think of that as a spring that's being stretched. It's not happy to be stretched. It wants to bring back the plus with the minus. You see here, it's uniform. So let's use what we have done just now to try to find the electric field. There's some charging here. See, this is a capacitor. It can hold charges. So it's storing energy in the electric field. That energy can be burped out. Okay? So now I'm going to do the capacitor. You can help me. Okay, so I have two plates. Are you with me? The goal is to find the electric field between the plates. So plus, 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 minus, 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 minus. So from this plate, the electric field goes where? How? Away or in? Away. Very good, right? So it's being blown. So I'm gonna do away here. 1, 2, I'm gonna do 4. And 1, 2, 3, 4, 5. But it should be equally spaced. And then away this way. Do you agree? That electric field, we know what it is. It should be sigma over 2 epsilon 0. We just have seen that before by taking the limit. Okay, and then you have the electric field from that one. Okay, and that's going to be what? Toward or away. So minus suck, right? Suck in. So it's going to be toward. So always toward, minus away from plus. Because plus gives out good vibes and negative, suck your energy. So bad vibe. Toxic, Some people are toxic. They are very tiring. It goes this way. But it worked also this way, right? So it's going to be toward, 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 toward. And the plus in this area here, it's going to be away, 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 away. So the blue one, which is from the negative, it's going to be also sigma over 2 epsilon 0. So it's uniform. They have the same magnitude. So what's going to happen outside of the capacitor? You have 3 to the left and 3 to the right. So that's going to be 0. 3 minus 3 is 0. Same thing. Left, right, left, right, left, right. Bye-bye. And here they add up. So the electric field between the plates of a capacitor will be, you have 1/2 and 1/2. It's going to be sigma over epsilon 0. So that's going to be the electric field between the plates of a capacitor. Agree? So it's just an application. And you see, it does not depend on the distance. And again, sigma will be the charge divided by the area. So that will be positive charge. That will be minus Q. Plus Q minus Q. Okay? So here you have a capacitor. For each plus, you get a minus. The electric field is uniform. And it's going to be sigma over epsilon 0, which depends on the area. You can increase the area. If you increase the area, you see electric field decreases. If you decrease the area, it's going to increase. Okay, so we have this here. Okay, so and then something very important, because you for test one, you always want one problem. My feet numb. One problem about torque, one problem about the dipole, always. So a torque from physics 1, it's a physical quantity that will measure how efficient a force is in making rotation happen. Okay, so if there is a torque, there is a rotation. How good is the rotation depends on the force, on that angle here and that distance there. So imagine this is a door. So here you have the door. This is the hinge, and you are pulling this way, and the door is going to open. The force is perpendicular, then you get the maximum torque. If the force is along here, you have zero torque, obviously, and then the orientation here is theta. Okay, so the definition of torque is going to be, so that will be the torque of a force F about the axis Q. So a torque is always about the axis. Okay, so it takes you back to physics 1. So I'm not going to reteach physics 1 again. You can find a video on my YouTube channel. So the torque will be R, the distance between the axis and where the force is applied, times the force, times the sine. And that's where it gets tricky, because the sine is the angle between the distance, that distance here, R and F. And they try to trick you sometimes, because you know the complementary angle. So sometimes you want to use cosine instead of sine. So how do we find this angle there? You take those two vectors, okay, R and F, you attach them by their tails, and that will be the angle we are talking about. So this is the angle, and that's going to be the angle between F and R. Is that clear? So again, this is the door. Imagine this is the door. This is the hinge of the door. You apply a torque, and it's gonna rotate. That will be counterclockwise. So it wants to rotate counterclockwise. Then you take your right hand. That's a cross product, right? You take your right and you go along R, and then you curve toward F. Right? So that means the rotation will be counterclockwise, but you see my thumb is towards you. So that's going to be the direction of the torque. The torque is a vector because you are doing the cross product. So when you are crossing R and F, you go along R, you curve toward F, and the torque will be out of the screen. Okay, that's how it works. So you see it wants to go counterclockwise, okay? This way, torque that way. The vector is towards you. That's called the cross product, and there is a tutorial again in my Dropbox, and we're going to do it this way. A point means it's towards you. If you see a cross, is away. So imagine you have a pen. Okay, the pen here is a vector. So if it's towards you, you see a dot. If it's away from you, and if it's like an arrow, and then you see a cross. Is that clear? From physics 1. Now you can take your 3 fingers instead. Okay, so when you are crossing two vectors A, B to get C, you go vector A, B, the angle can change, and that will be C. A, B, C. So that will be very important for what's coming up next, and that's called the right hand rule. Okay, so I highly recommend that you watch those tutorials, because anyway, you will have to take calculus. So anyway, this is called a dipole. Remember, we talked about dipole? Like a water molecule, for example, is a permanent dipole. You will have 2 electrons on one side, and then you have the hydrogen, the 2 hydrogen on the other side. So the charge here is the same. One is negative, one is positive. Okay, remember dipole. Dipole, you have the same charge here, and the electric field goes from plus to minus. So this is a dipole. The both charges have the same magnitude. And we did that last time. We defined a vector P. We call that the dipole moment. So it's a new physical quantity, Coulomb meters. And that vector goes from the minus to plus. Is that clear? So when you have a dipole inside an electric field, remember what the plus wants to go with the electric field or against? With, because it's positive, he wants to follow everyone, like he doesn't want to, blah, blah. Okay, good. So the plus wants to go with the electric field. Okay. Okay. Minus wants to go against. Do you agree? I hope they stop. Okay, so anyway, is it going to stay or is it going to rotate? It's going to rotate. Which way? Clockwise or counterclockwise? Clockwise. Clockwise. So if you do clockwise, where is the torque? Where is your current? Toward the ball, right? So the torque, you're going to show that with a cross. It's going to be inside. Oh, great. So that will be your torque. So you see, you are crossing P, E, and you get the torque. Okay, so I'm not going to do the math. You can do that. But you see, this is the definition. If you have a dipole inside an electric field, okay, you're going to get rotation. There will be a rotation, so there will be a torque. And the torque is by definition P, okay, so the dipole moment cross E. Okay, and so the magnitude is P E sine and sine theta. That angle is the angle between P and E. Okay, it's just a definition. You can show the math. So how can we remember what will happen? Is that you see that P here? You see that vector P from minus to plus? It wants to align itself with the electric field. That's what he wants to do. It's not happy. So it worked like the seed in castor oil that you sprinkle them in castor oil, you apply an electric field, and all those little seeds wants to align themselves with the electric field. So there will be a torque. Shh, quiet. Stop it. Oh, yeah. So you see those, this is charge here. You have castor oil because it's thick. You have those little seeds here and they will get polarized. Okay, so they get polarized and there will be a torque applied. I think it's broken. So you see that little seed here, minus wants to go here, plus wants to go there. So you have a minus and a plus, and it will get polarized, it will rotate such as it will align itself with the electric field. Is that clear? Oh, stop it. Okay, let's try to do this one. Someone has a baseball bat there? Try. Okay, let's try to do this one. So you have a dipole inside an electric field. So the first thing, and there is a problem like this for test number 1. So the first thing you want to do is to draw P, the dipole moment. Okay, and the magnitude is Q times the distance between them. But it goes from minus to plus. Okay. So that will be your P here. And I don't want to go down. So this is P and this is E. And why is it that it's going to be tricky? What's going to be the angle between E and P? That's the issue. What's going to be the angle between the vector P and the vector E? Huh? 35 or 145? Okay, so E is this way and P is that way. Do you agree? So I'm going to attach them by their tails. So we have E this way and then P going this way. So it's going to be 145. Okay, that's the only tricky part. Because if you don't see that, you're going to do cosine instead of sine. You're not going to get the right result. So you have to be very careful that when you're going to use the equation, the torque is magnitude of P, magnitude of E times the sine between the angle between E and P. You have to be very careful that you have the right angle. Nya, 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 nya. P is Q times the distance times E, and the angle will be 145. So, okay, now you can do the computation. Are you going down by any chance? Where are you going? Because if you are going down, can you tell them that we have an issue? If you go down to the library, yeah, to the library. Okay, can you find plug in? So we have Q, electric field, and we have the distance. Oh, by the way, I did I? Okay, I skipped some questions. What do you? Oh, look at that! It stopped. I hope it didn't go down. Can you check if he went down? No, just if you see, call him back. He's gone. I'm sorry. Okay, so the force. So there is a force. So how does the negative charge goes? Against or with? Against, right? Has a critical mind. Everything you tell it to do, it goes the opposite. And this one is with. So if you find the net force, what's going to be the net force? You have the same force left and right. So what's the net force? 0, right? 5 pounds to the right, 5 pounds to the left. The net force is 0. So the answer is 0. And then the magnitude of the electric dipole moment. So you just plug it in. So it's going to be Q times D, right? So it's going to be 1.6 times 10 to the negative 19. And the distance is 0.125 times 10 to the negative 9, right? And the unit is Coulomb meters. P is a dipole moment. P is a dipole moment. It's a vector that goes from minus to plus. And we do that because it's used in chemistry a lot or biology at a small scale. And the distance here is too small. So when we do computation to see the rotation and things like this, we use the dipole moment. It's easier to handle in the computations than just using the distance and the charge. So then you look at a chemistry table and they will tell you the dipole moment for each molecule. Like chloridic acid also, HCl is also a permanent dipole. And you can find that in the textbook. So it's going to be 2 times 10 to the negative 29 coulomb meters, right? Did you all find that? Okay. And magnitude and the direction of the torque. So we just have to plug that here. So P is 2 times 10 to the negative 29 times the electric field is what? 5 times 10 to the 5. And then here you have a sine 145. It's a 29 here. I don't know if you can see. Right? Did you get 5.74 times 10 to the negative 24 Newton meters? 4. It's a 4. Did you get that with the TI? 2e minus 29. That's a minus 29. It's a minus 5 times 10 to the 5 sine 45. You get this, okay? Minus 29. Minus 29 here. That's P. That's the dipole moment. And I forgot to mention that the unit is Newton meters. Okay. So the torque by definition is P cross E. Okay. So you need to review torque. Okay. And then they ask you which way it's gonna go. Direction. So it goes, where does it go? It goes, which way it's gonna rotate? Counterclockwise, so the torque is towards you. So it's gonna be a dot out of the screen, okay? Towards you. Okay, and then next we see that those things, the dipoles are unstable. And when something is unstable, that means they have a high level of energy. What kind of energy? It's potential energy. It's stored energy, right? Because if you let go, all that goes to rotational kinetic energy. So it's not happy. It has a high level of potential energy. So it wants to rotate and then it will be happy. So we can have the equation. So you have thank you. So an equation for the potential energy of a dipole inside an electric field. And we're going to go into details, but the equation is P dot E. It's a dot, okay? So now we have a dot product. So that means it's going to be a scalar. So why don't you try to do that? Okay, so the potential energy by definition of a dipole inside an electric field is going to be P dot E and it's scalar. If the dipole is against the electric field, it's very, very unhappy. It has a very high potential energy. If it's aligned with the electric field, now the potential energy is minimum and it's happy. Okay, so everything wants to go to a lower level of energy. So if I let go, this is lower energy. So just plugging in and let's find the potential energy of the dipole. Okay, so potential energy notation is U. It's going to be by definition minus P dot E. So what is a dot? A dot means the magnitude of P times the magnitude of E times the cosine, the angle between P and E, which is 145. Okay, so the potential energy will be minus P2 times negative 29 E 5 times 10 to the 5. Is that right? Cosine 145. So you see, it can be tricky because don't confuse the cosine and the sine. And what else? Okay, so potential energy is, what is the cosine of 145? Is that negative? Cosine 90, yeah, so it's going to be a negative. This is negative, do you agree? Okay, this is negative. So it's positive. So the potential energy is positive, which means it's not happy with life. Doesn't like to be positive. It wants to be negative. So we do those computation and you get, yeah, get what? 8.2? 8.19 times 24. 8.2, yes, times 10 to the negative 24 joules, because it's energy. Energy is in joules. Is that clear? So a water molecule, for example, we used to call that the Mickey Mouse, because this is minus, this is plus. This is 2 minus, right? So it's a dipole. You combine them, it's a dipole between 2Q and one is negative. So you have a dipole for the water molecule and you have a number and you look at your table in chemistry and you have the dipole for the water molecule. Okay. So and you have one like this for the tests for sure. So that means if you have an electric field this way and you have a dipole, it doesn't have to be a permanent dipole, right? So it can be polarized. So it will get polarized. So if you have minus here, for example, so this is plus. So this molecule wants to go to the plus because it goes always from plus to minus. Let's say you have a seed, okay? So it gets polarized because plus wants to go to minus, minus wants to go to plus. Okay, so you have a small dipole here, and it's not happy with its life. It will rotate such as it will align itself with the electric field. And in that case, it will be happy. Okay, because somewhere here you have plus, somewhere here you have minus. So this is perfect. Configuration, the lowest potential energy possible. Okay? It works for non-permanent molecule that get polarized or permanent molecule that already are polarized. Okay, definitively one question like this. Which one has the lowest potential energy? This one? Mm-hmm. Because I told you P goes from minus to plus and it wants to be aligned with the electric field. Aligned like collinear, not only collinear but showing the same direction. So it will be configuration. Huh? Which one is a line and with the same direction? The second one. Okay, so that will be the minimum potential energy. Now it's happy because you remember an electric field goes from plus to minus. So minus is facing plus, I'm happy. Plus is facing minus, I'm happy. That will be the maximum potential energy. Okay, not happy. Okay, because it's opposite direction. And we say because when you have potential energy, you need to define a reference level. So in physics 1, you could say potential energy is 0 here on the table. So you need a reference level. So potential energy is always defined depending on your 0 reference level. So we define the potential energy to be 0 here. That will be negative, that will be positive, and that will be in between. So potential energy is energy that depends on the configuration of a system. And we always talk about the change in potential energy or potential energy relative to a reference level. So gravitational potential energy, you can take energy to be 0 at infinity, or you can take energy to be 0 on the Earth. It's up to you. Depends what will be easier with the math. Okay? Yes. Why is the blue vector tick? Because that's how we define the dipole moment. Dipole moment is a vector that goes from the minus to the plus, by definition. No. Even if you do not have an electric field, and if you have a water molecule, you still have a dipole moment that goes from the oxygen to the hydrogen. So it's a good question. It's a vector that exists on its own. If you place a dipole inside an electric field, it will rotate, okay, to get the lowest potential energy possible, so it will align with the electric field. Okay? And that will be the definition. So how in physics, oh, okay, easy to understand. How a microwave works. So microwave works only if you have water molecules. So if you try to heat up a stone, it's not going to work, right? You need something juicy. Because the water molecules are dipoles, permanent dipoles. There is a minus and a plus. And then inside the microwave, you're going to send a microwave because that's why it's called a microwave oven, because you're sending microwave. What's a microwave? It's part of the electromagnetic spectrum, and you're gonna have an electric field. Okay, electromagnetic spectrum. Light is made of a magnetic field and electric field. The electric field keeps switching up and down and up and down and up and down, up and down and up and down and up and down. So if the electric field inside the microwave will keep going from up and down and up and down and up and down, what's going to happen? The water molecule, it will rotate because it try to align itself with the electric field. So this water molecule, you learn that in chemistry, they have energy level of vibration, rotation, twisting. I forgot my chemistry. But they shake. And because they shake, it's going to heat up. Okay, and this is very cool here. You have a very nice simulation. Okay, so let's see. Single and let's just how do we turn on the microwave on? So you see the electric field of the microwave is oscillating. Okay, it's like a sine wave, up and down and up and down, and the water molecule try to follow, right? So it's going to rotate, constantly rotating, and that's how it works. And that's how you heat up the food. Just because it will not work if the water molecule will not be it's a dipole. You can heat up. Okay, so you get the idea. So that's why if you put a pie in the microwave, the crust doesn't heat up, the juicy thing heats up, and you burn yourself. Have to be careful. But physics saved the day, so you're fine. Okay, so if I'm not going to do the math, but how can we find this equation? So that will be the equation for the potential energy is by using the definition of work. Work is energy transfer. So you start from some orientation. So the angle is initial angle theta I, and you're gonna come and rotate it, right? Against its will. So let's say it's this way, you're gonna take the dipole, you're gonna rotate it. And the work that you are doing, okay, the torque that you're applying, then transfer energy from you to the dipole, and that's how we can find the potential energy. So you can see how it's done here, okay? So what's the work done when you are doing rotation? The work done is by definition the work times the angular displacement from physics 1. Okay, if it's linear, it will be the force times the linear displacement. Now it's the torque times the rotational displacement. Okay, so anyway, you get to that equation. And again, you need to open your textbook. But if you look at here, you have the definition of a dipole, the moment, the torque applied by the electric field on the dipole. Okay, that will be the magnitude, and that will be the potential energy here in magnitude. And I like this equation sheet. It took me a long time to find the ideal one. Just here, they make a mistake, but you have the definition of a dot product here. You have the definition of a cross product with the components, or the magnitude of a cross product, and that will be the dot product. So for both cases, you can use the magnitude and the angle, or you can use the components from physics 1. See, electromagnetic wave has a component here, it has the electric field and the magnetic field. So anyways, just to make sure you know how to use, and see here, the dipole moment is Q times T. Capacitor, parallel plates, sigma over epsilon 0. So we did all that. Okay. Bless you. Where am I? Okay, so that's done. Okay, in which configuration it's the greatest? What did you say? So you go from minus to plus, you get the vector p. If the vector p is like opposite and linear, that will be the lowest, the greatest, the highest potential energy. If they align with each other, that will be the lowest. So we want the greatest, where it's not happy. It's very upset. The greatest means it's not happy because potential energy wants to be as low as possible. E, very good. Okay. So the greatest potential energy is when it's not happy, it wants to go to a lower level of energy. So anything like chemistry, physics, everything wants to go to a lower level of energy. So E will be the greatest potential energy, A will be the lowest, and those are in between. Okay, so if I take D, for example, if I take D, and let's say you are not sure which way it's going to rotate. So you take the positive charge. Positive charge wants to go with the electric field or against. Positive charge wants to go with, right? Because it's positive. It doesn't like to say no, cannot say no. Electric field love to say no. So it's going to go this way. That will be F. Another F. So which way it's going to rotate? Huh? It's going to rotate clockwise, this way. So if it rotates clockwise, then you're going to have the minus. That's a minus here and the plus there. And now it's happy because P and E are aligned with each other. Okay? Mhm. Because the minus will be here, the plus goes there, so P will be aligned with E, and then it's happy. So if it's clockwise, that means the torque will be into the board. Is that clear? Okay. So dipole wants to go, so here the dipole goes this way, it's not happy. It works also with magnetism. When you have a magnet inside the magnetic field, it wants to align with the magnetic field. And when it's rotating, it's going to release energy. So when the water molecule rotates, it's going to release energy that goes into heat. Okay, so lots of applications. So here it says do example 21.13. So that will be from your book. So that's what you need to do that on your own. Lot of applications. So those fish here, I don't know what it's called. It's a weird fish, knife fish. And they live in murky water, so they cannot see well. So they behave like a dipole. So they make their own electric field. And that's how they can sense, they can probe their environment. And I will explain why. They can sense if it's something juicy to eat, okay, something alive or something like dead. Not interesting. They can do that with this. And you have another fish. So the two fishes are not the same because it depends. Like this fish. So I don't know which one is that. I don't know if it's the same one as this one, but some fish, the positive is in the head and the negative is in the tail. And other fish who can do electrolocation, it's the opposite. The minus is here and the plus is there. So in that case, the head is what? Positive or negative? Positive, very good. Okay, electric field goes from positive to negative. And then I can try to explain why, but just memorize for now. If you have an insulator inside an electric field, like a stone, like something not alive, so it's an insulator, the electric field will get weaker. It doesn't disappear, but it will weaken the electric field. You see, you have less line. If you place a conductor, something alive, that he can eat, so conductor, juicy thing inside like us, right? Then the electric field will get stronger. So that's how the fish knows that it can eat or not eat. Okay? Because I don't know if I have a picture. So if it's something it can eat, so if it's something juicy, maybe another fish or something like this. So this is a conductor. And I told you that inside the conductor, you cannot have an electric field. So all the free electrons will rearrange themselves such as you cannot have an electric field inside. So the minus wants to go this way, right? So you have free electrons because it's a conductor. Do you agree? Conductor have free electrons. So all those electrons will go this way, and then it will be left here positive. Inside, you cannot have any charges. It's like Travolta, he rubs his feet against the floor and then he gets charged, but the charge goes on the outside. So what's going to happen? All those electrons here will have their own electric field. So it will make the electric field stronger. It's like a lens, right? So now the fish knows that this is good to eat. So if you have a conductor inside the electric field will get stronger and the fish knows, okay, this is juicy, this is good. Now, if you have an insulator, so you can see here. So if you have an insulator, it's called a dielectric when you go electrical engineering, then it does the opposite. It will it will make the electric field weaker. The conductor will make the electric field stronger. And I don't know if I can explain why is that. And it's also nice to understand that because this is very nice. Okay, so when you have an electric field, so this is a capacitor, but forget about the plates, goes from plus to minus. This is a capacitor. Now, if you place in between an insulator, everything inside will get polarized. So you're going to have a plus here and a minus there, and it will go against the external electric field. What you get at the end is a weaker electric field. It's not a great picture. Let me show you this picture is much better. Okay, so you have the electric field here. So this is called a dielectrics. So dielectric, you have a material which is an insulator. So the electrons cannot move inside, but the molecules can get polarized. So they can be squeezed, right? You see that they are squeezed? So this side here will be negative. You see, you have all negative. Here you have plus, minus, plus, minus, plus, minus, plus, minus, nothing happened, and you are left here with a positive. So the dielectric is going to generate an electric field on its own. So this way. And then you have the external electric field going that way. So it's not that they cancel each other, but you see they are opposite to each other. So it will get weaker. Okay. So inside, it's going to be a weaker electric field. The electric field will get weaker inside. Got that? Because insulator can be polarized. A conductor, the electrons are free to move. So it's important if you go electrical engineering because you need to use dielectrics inside capacitor to make them stronger, make more charges. So anyway, I hope it's not too confusing. You can just memorize it. So if you have a conductor, it will make the electric field stronger for pop quizzes. If you have a insulator, and then someone in marine biology explained to me that you have two kinds of fishes, one with a plus here and the minus there, and then the other one. So you have the elephant fish, and this is the knife fish, and this one is the opposite. The plus is here and the minus is there. If you are in marine biology. Exactly. Okay, so insulator, the electrons cannot move freely. Okay, so you can have an electric field inside the insulator, but the molecules can be polarized. So you end up with pluses on one side, pluses on the other side. If you have a conductor, you cannot have an electric field inside. So the free electrons will arrange themselves such as there is no electric field inside. So it will make the electric field stronger. Right? Are you with me? A lot of application in biology. Everything in biology is electrical in nature, but they don't tell you that. They don't want to say it's all physics, but actually, if you really look at the fundamental, it's all physics. Sorry. So you see here, you have a neuron. So neuron that make up the nervous system. And when you have a signal moving along that neuron from your hand to the brain to your hand, what is it? It's just a wave of traveling voltage. Okay, it's a voltage that will change up and down and up and down. So how is it done? You can have more plus here and less minus, less plus here and more plus there. So outside the cell, it's going to be positive. Inside, it's going to be negative. So here, it's not happy. You're going to have a very strong electric field between the plus and the minus. When there is a signal that will be sent, those little channels here open up. So of course the plus, they rush to get to the minus and they overshoot. So that's going to be minus and that's going to be plus. And then again, so what will happen is that you have a wave of plus minus plus minus plus minus because those ions move in and out and in and out and move in and out. Okay, and this is called action potential. Okay, it's sodium potassium pump. And if you want to know more about it, you can look it up. But it's all about electric field at a small scale. Okay, everything in biology is about electric field. And then the way ATP is made, it's produced by the mitochondria. Right? You all know about mitochondria. It's like a small factory that make ATP, which is energy for the body. And the way it works, it also has to do with electric field. So in that case, this is a membrane. This is the membrane of the mitochondria. And you have an electric field that goes from here to there, so down. And what's going to happen when you burn energy, like you are burning ketones or you are burning sugar, okay, electrons will move from high potential energy to a lower potential energy. So energy is released, and this energy is being used to move those positive charges against the electric field. So they get very upset. Now they have a high potential energy because they were pushed against their will, against the electric field. And then the only way they can go back along the electric field is to load go through these little things here, which I don't know the name, and that so they go through that opening there that will make something rotate. So you have mechanical energy, so electrical potential energy to mechanical energy, and that will combine phosphate something to H plus, and you have ATP. That's how it works. Isn't that amazing? At a small scale, it's totally fascinating. And you do have an electric field here between the plus and the minus. So you force the protons against the electric field, and then they get upset, so they want to go back to a lower potential energy. That energy being burnt out goes to mechanical energy and then to ATP. So that's why some people they take creatine, because creatine will make more phosphate and then it makes the things more efficient. So you can create more ATP. There is a video, but I'm not just quickly. So the electric field is from here to there. So they go against the electric field. The electric field goes from up and down. They are at a high level of potential energy. They get very upset. Blah, 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 blah. They go through here. There is something that will rotate and phosphate something, and then you have ATP. Super interesting. And then when you take creatine, you make this more efficient and faster, right? You increase the making of ATP. Super interesting. And what they don't tell you either is that where does that energy comes from? It comes from electron going from a high level of energy to a low level of energy when you are burning sugar or ketones. That's how it works. So the most fundamental things is understanding electron. It's all about electrons. It's all about electron transfer. Another application. So what do you think? These are pieces of DNA. So the electric field goes from what to what? Plus to minus or minus to plus? plus to minus. So these DNA pieces here, they go against the field. So that means they are charged what? If they go against, negatively charged, okay? And apparently it's what DNA is. I mean, they are all negatively charged. Little pieces of DNA goes against the electric field, and then it's inside some viscous liquid. So they will reach a terminal speed, but the heavier one will, it will take more time to, so they will lag behind. And the small one will go, larger will reach a terminal later and lag behind. So anyway, that's the idea. You use that. I know that at BBC they have that in the lab. Okay, a lot of application. So when you force a positive charge, okay, to go against the electric field, you need to provide energy. When positive charge goes with the electric field, it will do the opposite. It's going to burp out energy. So the idea of the semiconductor, it's a p-n junction. So what's the idea? The idea is to introduce an energy gap. Okay, so the current will not be able to go through unless they go above the energy gap. So that means that way you can control the current. Okay, so it means, so it's a p-n junction. It can be a diode, right? So you have the electric field this way, and let's say you connect that to a power supply. So this is plus and this is minus. And all those little positive charge they really want to go to the other side because they want to go to the minus, but they can't because there is a gap. Okay, this is an energy gap, right? So they have to go against the electric field. If you provide enough voltage, then they will jump the gap. Okay, and that's how we can control electricity, right? It's like transistor. Unless you apply a given voltage, enough for the charges to jump over the gap, then nothing goes. So then you have 0, 1, 1, 0, 0, 1, 1, 1, right? That was the revolution. So when you have a semiconductor, this is the electron here. This is the conduction band. You need help them to jump the gap, and then they are happy. So that way you can control the current. So it's jumping the gap. So anyway, when you take electrical engineering and you study transistors, MOSFET or whatever it's called, it's all about electric field. You have to know about electric field, and you have a lot of application. Did you survive? Gauss law. Okay, this is for the test as well. I'm going to try to explain it as simple, as easier as I can. Gauss law is not easy. Gauss law is just a mathematical tool to find the electric field when you have a nice symmetry. So I'm going to introduce that to you. Buckle up and bear with me. So he was a mathematician, Gauss law. And of course, you have your textbook that you need to open. You know how to study from a textbook? You start with the summary at the end. You start reading the summary at the end. And then you ask yourself questions. What do they mean here? What do they mean there? And then you go back. You look at all the pictures and you read the comments, right? What they say underneath the pictures, okay? And then you go through the chapters and you do the solved problem. Okay, so do you remember the plasma ball? Can I show you that? So let's say you have a charge here. It's a Tesla coil. Okay, so you can, it's like a Van Graaf generator here. So this is, let's say it's positively charged. And I show you that thanks to the gas inside the plasma, we can visualize the electric field. Can visualize it. And around it, And you see, at a distance, given distance, the electric field is the same. Okay, they are equally spaced at a given distance. And as you move away, you see the electric field is going to decrease. Okay, this Coulomb's law. So if you take a here at that distance here, the electric field will be stronger than that distance there. Yes, and there is a glass. Remember, it's a globe. So if I take okay, so imagine you have the glass. I want yellow. How can I get yellow? Okay, so there's a glass here, right? And the glass is a closed surface. So it's 2D. Do you agree that it's a closed surface? Okay. Now imagine now that this glass is an imaginary bag. It's you imagine it. It's imaginary. And we're going to call that bag here, which is spherical in that case, what we call the Gaussian. It's going to be called the Gaussian surface. Okay. And I can find how many electric field lines are poking through the surface. Okay, so the word is poking through. And the surface is closed. Okay, so it's a closed surface. Okay, so the number of electric field lines poking through that closed surface, which is in my head, it's imaginary. Okay, we call that in physics the flux, the electric field flux. And you can use also that physical quantity if you are studying hydrodynamics, right? Fluid mechanics. So just the number of fluid poking through that closed surface is going to be called the electric flux. Okay, that number of lines, do you think it's going to change now if I take I lost my yellow. If I take a smaller surface here, do you gonna get the same number of lines poking through? Like one, how many poking through here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. How many poking through this one? 1, 2, 3, 4, 5, 6, 13. So the number of field line poking through is the same, right? The electric field is not the same, it's going to be stronger. The surface is going to be smaller, but the number of electric field line is the same. Agree? Agree? Okay. So what do you think it depends on? So the distance will be for the electric field. Just how many lines poke through. If I want to increase the line, what should I do? Increase the voltage, so increase the charge. Okay, so if I increase the charge, if I multiply the charge by 2, I'm going to have twice the line. Agree? So we're going to see Gauss' law says that that flux, the number of electric field lines poking through that bag depends only on the charge. But if I try to write in white, charge inside the closed bag, don't call that a bag, over epsilon 0. Okay, that's all there is to it. Okay, and this is a consequence of Coulomb's law, because we're going to see, I will show you why, but in that case, you see the electric field flux, it's the area times the electric field. So a flux is always the multiplication of the area times a vector. So we're going to see that. But you see that if you divide the distance by 2, Okay, the area will be divided by 4. Okay, because the area of a sphere is 4 pi r squared. And if you divide the distance by 2, the electric field will be multiplied by 4. So it's going to stay the same. So that law is just a consequence of Coulomb's law that says if you divide by 2, the electric field is multiplied by 4. You follow? Okay, so this is Gauss' law in a nutshell. If you understand that, it's good. Then you're good. Okay, so then there is a pop quiz, and I